Adiabatic bomb calorimetry is an old experimental technique derived from Antoine Lavoisier's 1782 ice calorimeter. This technique, still in use today, is a very powerful technique that allows for the experimental determination of the heat released or absorbed by chemical reactions under constant volume conditions. So, technically, using an adiabatic bomb calorimeter, we will be able to determine the standard reaction energy change, delta RU standard, for a chemical reaction. In the course of today's lecture, we will show how we can relate the heat of reaction measured at constant volume, that is delta U for the reaction, to the heat of the reaction measured at constant pressure, that is delta H for the reaction. First, let us describe the various elements of an adiabatic bomb calorimeter. The calorimeter consists of a thermally insulated shell, shown in green on the schematic, which prevents heat from entering or leaving the enclosed space. Hence the use of the adjective adiabatic. Heat is generated or absorbed by the chemical reaction taking place in the sample cavity, shown in red. The sample cavity is generally enclosed in a very strong, thick-walled steel box called the bomb, shown in brown. Such a design allows explosive reactions to take place in an environment that is safe for the scientist making the measurements. Heat released or absorbed by the reaction is trapped inside the calorimeter and can only be exchanged with whatever resides within the calorimeter shell. To learn about the heat of reaction, we will therefore need to measure any temperature change inside the calorimeter. This is accomplished using the thermometer shown in yellow. To allow for an accurate measurement of the temperature change in a relatively short period of time, the calorimeter is filled with water and equipped with a stirrer so heat can be distributed homogeneously within the calorimeter walls. Calorimeters are often used to study combustion reactions, so they are usually also equipped with firing leads that generate a spark to trigger the reaction. Since the process is adiabatic, the total heat is equal to zero. However, the total heat can also be expressed as the sum of the heat of reaction plus the heat associated with the change in temperature for the calorimeter parts plus the heat associated with the change in temperature for the water. So we write Q reaction plus Ccal times delta T plus mass of water times specific heat capacity of water times delta T equal to 0. Ccal is the heat capacity of the calorimeter without the water, which we will call the empty calorimeter. The product mass water times specific heat capacity of water is the heat capacity of the water. We usually separate the heat capacity of the empty calorimeter from that of the water because whenever such calorimeters are used, variable amount of waters can be utilized, whereas the calorimeter parts are always the same. So in a typical experiment, the user would measure the mass of water placed in a calorimeter and measure the temperature change delta T. A priori knowledge of the empty calorimeter heat capacity, Ccal, and of the specific heat capacity of water, 4.184 joules per gram per degree Celsius, will allow us to determine the heat of reaction. This equation also tells us that if the reaction is carried out in the calorimeter is exothermic, then Q reaction is negative, and the temperature change delta T for both the calorimeter and water is going to be positive since heat capacities are positive. So, for an exothermic reaction, the temperature in the calorimeter always rises. On the previous slide, we derived the relationship between the temperature change in an adiabatic bomb calorimeter, the mass of water, the heat capacity of the calorimeter, and the heat of reaction. To be able to solve for the heat of reaction, Q reaction, we need to know the heat capacity of the empty calorimeter, which we called Ccal. In other words, we need to calibrate the calorimeter. Two methods are routinely used to calibrate a calorimeter. The first method consists in running a combustion reaction in the calorimeter for which we know the heat of reaction. Measurement of the temperature rise delta T as a result of the exothermic reaction will allow us to determine Ccal. The second method, to be described next, consists in using a resistive heater to transfer heat into the calorimeter. The heat released by the heater, which we call Q heater, can be written as the product of the current intensity, I, the applied voltage, V, and the length of time the current is applied, T. Alternatively, using Ohm's law, we can substitute the voltage V by the product of the resistance R and the current I, or substitute the product Ri squared by the heater power, P. In this equation, all physical quantities need to be expressed in SI units because we want to obtain the heat generated by the heater in the SI unit of energy, joules. So the electric current should be expressed in units of ampere with symbol A, the voltage in volts with symbol V, the resistance in ohms with symbol omega, the power in watt with symbol W, and the time in seconds, symbol S. Since the heat generated by the heater results in a temperature rise, delta T, for the empty calorimeter and for the water, we can write Q heater equals Q calorimeter plus Q water. The heat absorbed by the empty calorimeter is Ccal times delta T, while the heat absorbed by the water is mass water times specific heat capacity of water times delta T. Equating the sum of these two terms to the heat generated by the heater allows us to obtain an equation relating Ccal to quantities we either measure, I, V, T, mass of water, delta T, or quantities we know, like the specific heat capacity of water, that is 4.184 joules per gram per degree Celsius.